I'll wait another minute, see if other people want to get on. Okay, well, let me go ahead and get started. So today we want to discuss receiver operating characteristic curves. And so here we go. So in terms of the discussion, we're going to just spend a couple minutes on the concepts related to diagnostic accuracy. In a test where there's a dichotomous outcome and just the test is either yes or no. And then we will look at diagnostic accuracy if we have a continuous measurement scale. And then we want to look at area under the curve as it relates to logistic regression, and then talk about discrimination and calibration. So the basic idea here is to be able to diagnose. If I can get my, there we go. So in the situation where we have just this 2x2 table, familiar to probably most everybody, where we have a test that's dichotomous, either yes or no, positive or negative, and then we have the disease, whether the patient actually has the disease or doesn't have the disease. And so then we have our four cells: true positive, false positives, false negatives, and true negatives. And then we can calculate sensitivity, specificity, and then our positive and negative predictive values. So where sensitivity equals the number of true positives divided by the number of true positives plus the false negatives, and specificity, the true negatives divided by the true negatives plus the false positives. In other words, the totals there, the column totals are those that have the disease and those that don't have the disease. And then our predictive values, the positive predictive values, is where the denominator is the true positive plus the false positives, and our negative predictive value, the denominator is the true negatives plus the false negatives. So what if we have a test that's not dichotomous, but is either continuous or ordinal? And so a situation that we might have, or their test can also be dichotomous, as we'll see later on. But so if our scale, or rating scale, is ordinal, then the experts or the raters rate how likely the test indicates disease, and usually the the scale points are Likert scales, maybe 5 points or maybe up to 10 points. And then if we have a continuous variable, then we have a range of variables where high values or lower values would indicate a disease. And then we're going to have experts observers or raters or readers, as they're often referred to, indicate whether the scale indicates disease or not disease. So if we have ordinal or continuous tests, then we're going to select a cutoff value, and we're going to compute sensitivity and specificity for a specific cutoff. And obviously, changing the cutoff is going to change the sensitivity and specificity. So if we look at this in terms of a distribution where we have a continuous distribution, then the distribution on the right here is the distribution of diseased individuals, and the distribution on the left here is the non-diseased distribution. So if we have, take the area to the right of the disease distribution, so in other words, if this is our cutoff, and so the area under the curve to the right of the cutoff is sensitivity. For the non-disease distribution, to the left of the cutoff then is our specificity. And so in terms of the overlap here, if individuals that are to the right of the cutoff but are actually in the non-disease distribution, then those are the false positives. And similarly, if we have patients that are actually in the disease distribution but are to the left of the cutoff, then the area here represents the false negatives. So for ordinal tests, for where we have ordinal data, a rating scale, then the cutoffs are the actual scale points. So if you have a 5-point scale, then we're going to look at sensitivity and specificity at each cutoff. And then we're going to plot sensitivity with 1 minus specificity for each cutoff value, or that's the true positive fraction plotted against the false positive fraction. And so in our ROC curve would look like this. The vertical axis is the true positives rate, and the horizontal axis is the false positive rate. And so we would, if we have an ordinal scale, which say has 10 points, then you could see the points there, and then how we would connect those to get our receiver operating characteristic curve. So what we want to do then is we want to compute the area under the ROC curve. And of course, we refer to this as the AUC, or the area under the curve. And you can see the rectangles that I have drawn here that represent the area. And so we can do what's called the trapezoidal method, which just is computing the area of each of these rectangles, and that's our area under the curve. So the total area then is we're going to scale it so it equals 1. And then the closer the curve comes to the upper left corner, the greater the accuracy. However, if the curve is on or close to the 45-degree line, then we have less accuracy. If it's actually on the 45-degree line, then our area under the curve is going to equal 0.5, and that indicates a non-informative test. In other words, it's just a toss-up of whether or not the patient has the disease or not. And so we draw in here our 45-degree line, and then so if our ROC curve approaches the upper left corner, then we have really good discrimination. But if it's as close to the 45-degree line, then we have less discrimination or identifying the diseased patients. So in one application here we might want to look at different tests for a particular disease. And so we calculate the ROC curve from a sample of patients from the population of interest. And we calculate the AUC, the area under the curve, and its standard error. And then we can compare the ROC curves for different tests. So, for example, a CT scan versus an MRI. So when we compute the ROC curves, the AUC's standard errors is really straightforward, and most statistical package will compute this for you. For example, in Stata, three routines that we have are ROC tab, ROC fit, and ROC comp to calculate and compare ROC curves. But you'd have comparable routines in SAS and R as well. So in terms of our computations, there's two ways we can do that. We can use the non-parametric, which is, I mentioned before, the trapezoidal method, where we sum the rectangles underneath the curve. However, we can also do a parametric using the binormal model and use maximum likelihood to estimate the parameters of the ROC curve and the area under the curve. In that case, we would get a smooth curve, whereas we use the non-parametric, we'll get a curve that's not particularly smooth. One of the issues that we're going to look at here is that our software usually doesn't account for correlated data. And then obviously sometimes, as in other applications, maximum likelihood fails to converge or doesn't work. So, and the other then situation we have is not only we have multiple patients, but we might have multiple experts. In other words, experts that are going to rate the patients for different tests or on the same test. So if we have a sample from a patient population, that's what we call a random effect. That's a random sample, more or less, from the patient population. The different tests are going to be fixed. That is, it's just a finite number of tests. But the experts that we might have, if we have more than one, is going to be another random effect. So our design is going to be a random sample of patients with and without disease, and then a random sample of experts. And they're going to rate every patient for each test. And the experts or raters are usually, we're not so concerned about those because they're really a nuisance variable, but it needs to be accounted for in our calculations. So here's an example that we might have where we have 5 patients and 3 raters, and then we have, say, 2 different tests, A and B, and then we have the ratings of the raters, and then the last column is whether or not the person is actually diseased or not. So I want to go through a specific example to illustrate this, where we have multiple patients and multiple raters in the diagnosis of melanoma. And a sub-study of this was to look at the comparison of how accurate primary care physicians were versus dermatologists. And this was published a while ago in the Journal of Internal Medicine. So here's what the data is going to look at that the PCPs and the dermatologists are going to rate. So it's actual patients, but just pictures of the lesion. And so in this case, there are 30 pictures or 30 patients. of melanoma or possible melanoma lesions. And so the patients or the raters are going to rate each of the patients, in other words, the pictures, on a 10-point scale from highly unlikely to highly likely. And so there are two questions that were, the first one being, would you biopsy for the dermatologist? The question was asked there. And then for the PCPs, the question was, would you refer for a biopsy to the dermatology? And then question B is just simply for both, is it a melanoma from highly unlikely to highly likely? And so here's an example for one doctor, one PCP. And so we have the 30 pictures, and this is all for question A in this case. And then in the second to last column, we have the PCP's rating, and then the last column is whether it's actually a melanoma or not. And so this is that we would have this sort of setup for each of the PCPs and each of the dermatologists. So in terms of our ROC curves, we're going to have 10 cut points. Obviously, we have a 10-point scale. And we have actually quite a large sample size, 100 study dermatologists and 127 PCPs. And so each rater is going to have one ROC curve. And so if we were to plot the ROC curves for each of the doctors, the PCPs or the dermatologists, we would get graphs that look like this. And so just looking at the graphs, there's a couple things we can tell right away. One is for question A, and B, there's a lot less variability for dermatologists than there is for primary care physicians. And so as we would expect, the dermatologists are going to do better than the primary care physicians. And then we can also tell, at least for the dermatologists, that question B was, there's a lot less variability for that than there was for question A. So we're going to compute the area under the curve for each rater, and we're going to compare the average AUC of physician types. And so in this case, each rater has one AUC value, and so we can just do a simple t-test for differences in the mean AUC. But of course, what we're going to then deal with is the fact that we have 30 patients and we have different experts, different numbers of PCPs and a different number of dermatologists. So there's going to be a random error associated with each AUC. But if we just do the simple t-test, then we can see that there's a statistically significant difference between dermatologists and PCPs on both questions, with the dermatologists doing better than the primary care physicians. So how are we going to account for rater and subject variability in this? Because in our t-test, we've ignored this. So one method that's been proposed, and I have the reference here, is the jackknife method, where when we use the jackknife method for whatever we do, that means we're going to leave one out, compute our statistic with the other remaining ones, and then we're going to do that again, leaving out the second, in this case, patient, and recompute our area under the curve. So what we get then is a jackknife pseudo value AUC for each rater and each patient. And so the calculation, the formula I have there, we have 30 patients times the average AUC minus 29 times the AUC. And so the data for each rater will consist of 30 pseudo AUCs, each having left one patient out. And you can see from the formula here that it's possible that we might get AUCs greater than 1, or we might get negative AUCs, pseudo AUCs. And so here's the in the AUC column at the end there, that's actually the pseudo AUC. And so you can see that there are some that are greater than 1 and some that are negative. And actually calculating an AUC, the maximum number you can get is 1. But you might get a negative AUC. And what that means is that the test is doing the opposite of what you thought it would. In other words, if you're trying to predict those that have the disease and you get a negative AUC, that means that your test is actually predicting those who don't have the disease. But in terms of our calculation here to take account of variability of the PCPs and the patients, we calculate this pseudo AUC. And so then we can use just standard general linear model software to estimate and compare AUCs. And so this is, I believe it's R syntax here, where our linear mixed effects model is the AUC is modeled as a function of the doctor, either PCP or dermatologist, and then the ID is the patient ID, which is our random effect. And so we see gives you different statistics here, but the one that we're interested in is down here where we have the AUC models as a function of the doctor, and we see that there's a significant difference between doctor types, which is, the same conclusion we got with the t-test, but now we're taking into account the variability between patients. And so when we actually calculate the AUC, we can see that the dermatologists have a better AUC than the PCPs. So now what we're going to do is we're going to take into account both the patients and the raters, the doctors. So we have our random effect is going to be ID within pictures. And so again, we get a significant difference between the first model that we did before and the second model. So this random effect here is significantly better. What this means is significantly better than the one where we just took into account the difference between patients. And so this is just a continuation of our output here and giving us different statistics. But again, we see that this taking into account the pictures within IDs or within doctors is better than the model just taking into account the pictures of the patients. And so again, you can see that this is again plotting the individual ROC curves for each doctor, each rater. And as we mentioned, we can see that the dermatologists are doing better, and that are doing better than the primary care physicians, and that they're, at least the dermatologists are doing better on question B than they do on question A. And then we do the same analysis for question B and get the same result. This question B was just whether it's a melanoma or not. So we can ask the question then, is the area under the average ROC curve the same as the average area under the curve? And so what we're going to do is plot the sensitivity with 1 minus specificity for each cutoff, and compute the area under the curve for the average ROC curve in order, and do this using, we'll do it first using standard software, ignoring raters. And so this is what we would get, and we can see that the dermatologists on both questions have a better AUC than the PCPs. And so if we calculate the average AUC versus the average area under the average curve, we can see that it's pretty similar, a little bit of difference, but it's pretty similar. So the for question A, the average area under the curve is 0.75, but if we do the average area under the average curve, it's a little bit better. And then the same for the dermatologist, and the same for question B. So there are other statistics that in doing that we can use the jackknife to compare our, in this case, raters. And this is the likelihood ratio test, which is the likelihood of disease given a positive test to the likelihood of no disease given a positive test. And again, this is sensitivity divided by 1 minus specificity. And so we calculate a likelihood ratio for each cutoff. The likelihood ratio will be 1 for our first cut point. And so if we compare the dermatologists with the PCPs, we have can see that the likelihood ratio is better for the dermatologist than it is for the PCPs at each cut point, and that they're actually doing better over the whole range of cut points. And then we get the same thing for question B, is it melanoma, where the dermatologists are doing better with the likelihood ratio than for the PCPs. So basically what we conclude then is that the dermatologists have significantly better accuracy for both questions A and B, and that the accuracy for question B is higher for question A, actually for both groups, but more pronounced for the dermatologists. So the conclusions that we can make is that we can account for multiple raters and correlated data with hierarchical models where we have random effects. In this case, we have 2 random effects, the patients, which are always random effects, and then the raters, which we treat as a random effect. And so the way that we're going to analyze this is we're going to apply what we call a semi-parametric model to calculate the AUC. The jackknife part of it is a non-parametric test and then we use the general linear model using the estimate of variance we got from the jackknife in a parametric model. Okay, so now I want to end up by talking about area under the curve related to logistic regression. And so, as you recall from what we're doing in logistic regression, we have an outcome that's dichotomous. Dead, alive, yes, no, or disease, not disease. And the odds of the outcome is the probability of the outcome divided by 1 minus the probability of the outcome. And so then what we're going to model is what we call the logit, or the log of the probability divided by 1 minus the probability. And so in this case, our regression coefficients, our beta, are going to indicate the change in log odds of an event with a 1 unit change in the dependent variable, or the test, or whatever it is we're looking at, for a 1 unit change in the x variable. And this is complementary to just linear regression, where the betas in linear, regular linear regression are just the change of the value of the outcome with 1 unit change in the dependent variables, or the covariates. But in logistic regression, we're looking at the change in log odds. And so the sign of the beta determines whether the log odds is increasing or decreasing. If it's greater than 0, then we have an increase in the log odds. If it's negative, then there's a decrease in the log odds. If the regression coefficient to beta is 0, then we have no linear relationship between the log odds and our predictor variable. And then, as you remember from studying logistic regression, if we exponentiate the regression coefficients, the betas, then we get the odds ratio. And so what we're interested in, as we mentioned, the slope coefficient from a logistic regression, which is the beta, is the rate of change in the log odds of the event as the x changes 1 unit. And then we can get the probability of the event as our predictor variable or dependent variable changes. And we get that by dividing the exponentiated regression equation by 1 plus the regression equation. And then we can also do the same thing with multivariable logistic regression, where we have more than 1 independent variable, which can be dichotomous or ordinal, nominal, continuous. And so now the interpretation of our regression coefficients, our betas, is that we have the association between the predictor variables, the x variables, and log odds adjusted for all other variables in the equation. And as we did for just the single simple equation, the x, if we exponentiate the betas, we get an odds ratio. So this is an example from a study we did some time ago, where we wanted to develop a predictive model for 30-day readmission among PCIN patients, percutaneous coronary intervention patients. And so we had a number of variables that we wanted to look at as far as predictive model goes. And so, for example, for age, we have a significant effect of age, and we did age in 10-year units. So of course, what the odds ratio means here is that for every 10-year increase in age, the odds ratio is going to increase by 25%. And then we have some others down here that where we have an odds ratio less than 1, which means that our regression coefficient was negative. So, for example, if the procedure was elective, then the odds ratio is 0.59. So in this case, it means that those that have elective PCIs are 41% less likely to be admitted within 30 days after discharge. And then this, again, whether it's previous hospitalization or Hauser count, that's an indication of comorbidities. And we can see the effect of each of those. So what we want to calculate is how well our model here predicts the outcome, 30-day readmissions. And so we calculate what is called usually in logistic regression is referred to as a C-index. And as we'll see, that turns out to be the same thing as an area under the receiver operating characteristic curve. And so we get a C-index of 0.76 essentially. So that's in terms of our indication of how good our discrimination is. It's pretty good. It's not great, but it's if our C-index, just like our same thing as our area under the receiver operating characteristic curve, if it's 0.5, then we have no discrimination. Good discrimination is usually considered 0.8 or above. And then sometimes you get C-index or area under the curves that are kind of, I guess, what we call mediocre, sort of kind of in between 0.6 and 0.7. Although I've seen articles where a 0.65 was called, good discrimination, but anyway, be that as it may. And then in addition to the area under the receiver operating curve, we can calculate calibration. In other words, are the predictive probabilities equal to the observed probabilities? And so what we're going to do is have a plot of observed probabilities with predicted probabilities. And so in this plot, obviously, what we would hope for is a slope of 1. That is, we'd have our observed probabilities being exactly equal to the predictive probabilities. And so in our 30-day readmission, we did a bar graph here of the predicted readmission versus the observed proportion readmitted for each for quintiles. And so you can see that it's pretty good here in terms of the calibration, that our predicted probabilities are pretty close to our observed probabilities. If we do this, plot these as on a continuous scale, we would get, or what we would hope to get is something like this, where our calibration slope in this case observed is 0.97, which is pretty close to 1. So in this case, we would have almost perfect calibration. So the area under the curve, or the C-index, assesses discrimination of a test or a predictive model. And the outcome can be dichotomous, or it can be continuous or ordinal. And as we mentioned, we'd like to see an area under the curve, or a C-index, that's between 0.8 and 0.9. although in many cases, we're going to have to usually, if we find something that's greater than 0.7, we'll kind of be okay, or sort of be okay with that. I might add here, though, if we get a C index or an AUC that's in the high 90s, like 0.98 or 0.99, then we might want to, we might wonder about that. Is that too good to be true? And was something going on with the, maybe with the raters? But anyway, the both the AUC and the C index, as I mentioned, are the same thing, and we want to get that really high, where the as it approaches 1, we're having really good discrimination. As it approaches 0.5, we're getting not so good discrimination. Okay, and so I have then a number of references here that you might want to consider, that look at the area under the curve, and the jackknife method is one that I cited earlier. So I have a little bit of time, well, actually quite a bit of time, more than 15 minutes here. So if there's any questions or comments that you would have to make, I think, do we use, let's see, not the chat, but there's a Q&A tab that you have if you would like to make or have any questions or make any comments. So I'll remain on for a few minutes if you would like to ask some questions, or if you want to just email me questions at my MedStar email address. And so I might mention that we will have one more presentation in May for the academic year, and then we'll take a break for the summer. Okay, so I got a couple questions here. Let me deal with the last one first. The ideal cutoff is at the upper left corner. That's because if you think of the ROC curve, is the area under the curve is going to be the greatest the further the curve is to the upper left. And so you want to talk a bit about choosing between random effects and fixed effects models. Well, so the fixed effects are going to be the test that you're comparing. The random effects are going to be patients, and then if, as we illustrated, if you have raters that are rating the patients, or in example that I had the pictures of patient melanomas, then those, the raters are going to be random effects. And so whenever you have a ordinal or continuous indication of whether there's disease or not disease, usually you're going to have more than one person look at that because you have to establish reliability. And so those are always going to be random effects. But if you have just a dichotomous test, that is, on the test, you know whether it's gives a yes or a no for having the disease, and then you compare that with the actual disease. That's going to be just a fixed effect. So the random effects only come into play when you have raters or observers making a decision about whether the model or the test is indicating disease or not. So is that I hope that's helpful, or let me know if you have other questions. Okay, so yeah, if you have evaluating outcomes, then the providers are going to be a random effect. And so for another example would be if you just have, say, a straight linear model or an ordinary linear model, but you're getting your patients from different providers or, say, different hospitals or different clinics, then they would be random effects in your model, because those would be considered a random sample of all the possible providers there could be. So that's the same concept, whether you're looking at ROC curves here or looking at just a predictive, or you're looking at some model that's looking at a different set of a number of variables that predict a particular outcome, and your patients come from different clinics, then you would have two random effects patients, which are always random effects, and then the clinics or the providers would be a random effect. Okay, so in yeah, in random forest ingredient boosting, you have the same sort of thing where you can calculate the how well the model discriminates. Um, so discrimination and calibration are just are two different things of the for determining how good a model is doing, how good a model performs. And so for both of the random forest and gradient boosting, you can calculate an AUC, and you can calculate a calibration curve. The calibration being are the predicted probabilities. Equal to or at least close to the observed probabilities of disease or no disease. Yeah, let's see. I would let me look that up because for the data that I was presenting here, there was always complete data. But if you have imbalanced data sets, then that's going to pose a problem. So let me I'd have to look that up because I'm not sure how that works. So if you want to just give me your email, you can send that to my email here. Oops, wrong one. Yeah, just paul.kolm at medstar.net. Okay, all right, thank you. And I will get back to you.